Hi folks, we're going to take a quick look at how to describe the end behavior of a rational function, and it's going to be similar to the way we describe the end behavior of any function. Now I'll start off by saying that we're not using yet the more formal notation for talking about end behavior. Okay, so we'll look at some options here. First of all is to determine what the end behavior is going to be. So in this case here, we see that the degree of the denominator is higher than the degree of the numerator, so we know that eventually this function will approach 0. Okay, so we're just going to use the same notation as we did when we were talking about polynomials. So because the end behavior will be the same on either side, meaning as x approaches positive infinity and as x approaches negative infinity, because whether this number, whether the x's are getting very, very large positive numbers or very, very small negative numbers, the end result will be the same. It's going to be approaching 0. So what we can say here is as x approaches positive or negative infinity, so regardless of which direction you're going, we know that y is going to be approaching 0. So this is the way you can state the end behavior. Now, think about what a function looks like that has that type of end behavior. So it might be approaching 0, let's say from the positive side, let's say it's from the positive side again. Essentially what you have is a horizontal asymptote at y equals 0. Okay, so another way of stating this end behavior is to say there is a horizontal asymptote of y equals 0. This would be another acceptable way of saying the same thing. Okay. We're going to see that with other functions, you might have a horizontal asymptote which only is valid for one side of the function and not for both. But when it comes to rational functions, if you have a horizontal asymptote, the function will be approaching that line from the on the left-hand side and on the right-hand side. So two ways of describing the same thing. Okay? Let's move on to this one here where they're the same. Now, if all I'm asking you for is to state the end behavior, then I don't expect you to demonstrate algebraically how you can get to that. What we found was we found a pattern, and the pattern was that if the degrees are the same, okay, all the subsequent terms after the leading terms become insignificant, and we just focus on those leading terms. And it's going to approach, again, a horizontal asymptote given by the ratio of the leading coefficients. So we can say here, as x approaches positive or negative infinity, y is going to approach 3 over 5. Okay, so again here, let's see what that might look like. So say this is 3 over 5. Okay, perhaps it's approaching 3 over 5 from the top on that side there, perhaps from below on that side there. Essentially we have again a horizontal asymptote. So a second way of describing this end behavior is to say that it has a horizontal asymptote of y equals 3 over 5. Okay, again, equivalent ways of stating the end behavior. Now let's get to this last one here. Okay, we know that because the degree of the numerator is larger than the degree of the denominator, we know that this is going to approach either positive or negative infinity. Okay, now you might be asking yourself, well, do I know if it's going to be positive or negative infinity? Well, one option is to just stick a really large positive number for x and see if it gives you a large positive number, then it's approaching positive infinity, or negative number, negative infinity. Okay, that's one way of getting a sense of what's happening there. However, we know that when these functions are approaching positive and negative infinity, they don't just approach, in a random way. We know that they approach the quotient of these two polynomials. Okay, in this case here, the quotient is going to be a linear, so it's going to have a linear oblique asymptote. So by determining what that linear oblique asymptote is, we can then determine whether it's going to positive or negative infinity. Now, let me find this. Here we have to do a little more work than usual because we're dividing by a quadratic. We're not dividing by a linear, so we can't use synthetic division. Okay, so let's do that here. So we have x cubed plus 0x squared, don't forget the missing term, plus 3x minus 1. Okay, and we're dividing that by 2x squared minus x plus 0. So we always add in the terms that are missing. Okay, so we have to ask ourselves, what do I multiply to 2x squared to get to x cubed? Well, I know I'm going to need an x, but I'm going to need to get rid of that coefficient of 2. So I'm going to multiply that by, excuse me, 1/2 x. Okay, so 1/2 x times 2x squared is going to be x cubed, which is what we want. 1/2 x times -1 is minus 1/2 x squared, and then 1/2 x times 0, well, it's just plus 0. Okay, and let's subtract. And what do we end up with here? We end up with x cubed minus x cubed is 0. 0 plus negative, 0 minus -1/2 is just going to be 1/2 x squared. 3 plus 0, so plus 3x, and then bring down the -1. All right. So let's see, what do we need to multiply to 2 to help us get rid of this 1/2? Well, 2 times what number is equal to 1/2? Well, it's going to have to be a quarter. So it's going to be plus 1/4. So let's see, we get a quarter times 2 is 2/4, which is 1/2 x squared. Then here we have minus 1/4 x, and then we have plus 0. And so now, when we subtract this, we're not going to be able to go any further. Okay? In fact, this is going to give us my remainder. I actually don't need to know the remainder in order to find the end behavior. I just need the quotient. Okay, I can certainly find it, but I don't need it. What I'm interested in is in the quotient. Okay, because this means that as x approaches positive or negative infinity, y is going to approach the quotient of these two polynomials. It's going to approach the function 1/2 x plus 1/4. So this is one way of stating the end behavior. Okay, so what does that mean? That means that, well, 1/2 x, so positive slope, quarter y-intercept, so it's going to be some line that looks like this, and that means that the function at some point is going to be approaching that line. In other words, this is going to be a linear oblique asymptote. So another way of describing the end behavior is to say that this function has an oblique asymptote of y equals 1/2 x plus 1/4. Okay. Now, if you did want to know, you just look at this function here, and you realize, well, as x goes to positive infinity, my function has to also be going to positive infinity, because that's where 1/2 x plus 1/4 is going. As x approaches negative infinity, well, the y's are going to be approaching negative infinity, because that's where this function here is going as x approaches negative infinity. Okay. One of the things I want you to notice that when I'm describing end behavior, notice I'm only interested in the extremities. Okay. These asymptotes, whether they be linear oblique asymptote, whether it be a horizontal asymptote, has no effect on what's happening in the middle of the function. Okay. To determine that behavior, that's where you use the x-intercepts, that's where you use the vertical asymptotes, and what we're going to work on next time. Okay, so just to recap, number 1 is to know how to determine the actual end behaviors. So denominator greater degree has to be going to 0. Same degree, you just look at the quotient of the leading coefficients, and when the numerator is larger degree, you need to divide to find the asymptotic behavior. In this case here, the linear oblique asymptote. In order to describe that end behavior, you have a couple of ways. Okay, one is to use what we used before, the as x goes to positive or negative infinity, to describe either your horizontal asymptote, y is approaching a particular number, or in this case here, the y's are approaching a function, in this case here, a linear function, or to just specify what the asymptote is. In this case here, horizontal asymptote y equals 0, horizontal asymptote of 3 over 5, and an oblique asymptote given by this line. Okay, that's it for this one.